Good afternoon, everybody. We are going to get started in 5 minutes. I'm looking forward to talking to you today about the life and death of stars. Enjoy the pre-show. We'll see you in 5.
5, 4, 3, 2, 1, fire!
Time to launch the rocket. Our next program is commencing. I am excited to talk to everybody today. I'm feeling good. It's a beautiful, well, chilly day outside, but I saw the sun just for a second. It's nice to be joined by some old friends and some new friends. If you haven't been here before, my name is Ryan, and I'm going to be your personal astronomer, your guide to the universe. We are going to go and explore stars today, which means we're going to see how stars were born, where they were born, and how they kind of form and come to be, and how they make planets. And then we're going to go see how stars live their lives, like our sun. How does the sun live? How does it change over time? How do big stars live differently? Because they are quite different. And then the really cool stuff, how do stars end their lives? Do they end with a big explosion? Do they end with a sneeze? Depends on the star. So we have a lot of fun things to talk about. And, oh, hey, Jackson, thanks for joining us. To skip a bit of school today for the lesson. I'm so glad. Well, I mean, I'm not glad you're skipping school, but I'm glad you could join me today. I'm pretty excited. So let's get started. We've got 15 space adventurers with us so far, and hopefully we get a few more. So let's actually go and talk about the sun first. The sun is the star that we know of, right? And actually, you know what? I'm going to put her over here. The sun is in the sky. This is about where it is right now. For those who don't know, the sun is a star, just like all the other stars in the sky. The big difference between the sun and all the other stars that we see is that the sun is very close to us. The sun's very close to us. But if we get rid of all the air around the Earth, we can see all the other stars in the sky as well. And you can see that the sun really does look like a star. We do have some others, you know, we have the moon here. We have a couple planets that are very close to the sun, Venus and Mercury, and then that's Jupiter over there, and Saturn's a bit further down, right down there. Anyway, you can get a lesson, eh? By the way, one thing for anybody who is new or who doesn't know this, you can use the link to this stream and to any other streams of mine that you attend. You can rewatch them anytime you want. So you're watching live right now. I am really here. But in the future, if you ever missed something or you wanted to come and see some of the things that we talked about again, you can use that link and rewatch it anytime. Because I tend to talk fast, right? I don't want you to miss anything. And for those who are new, I'd love to hear you say hello in the chat. I'd love to hear some questions if you're curious about things. Let me know who you are and why you're here. Otherwise, you're more than welcome to just sit back and relax and enjoy. So let's go back and talk about our stars. There's our sun. And if we look at the sun in the sky, whoa, I wanted to zoom in on it a little bit. Let's go look at the sun. Looks like we might have a planet there. Oh no, there it is. There's the sun up close. Whoa, that looks a little different than we might have been expecting. We have these this bright glow around the sun and these dark spots. It's not the best graphic, but it works pretty well. These dark spots are called sunspots. And in order to really understand them, to understand how the sun behaves, we got to go look at it over here in Space Engine. And you can really see that glow around the sun. That's actually called the solar wind. The solar wind. And if we speed time up a little bit, you can actually see it blowing. It's literally blowing away from the sun. It travels all through outer space. And in addition to the light and the heat that the sun releases, it also releases these charged particles in the solar wind. And they can be pretty dangerous. If you go too close to the sun, I mean, not only is it really, really hot, not only is it really bright, but it can also be really dangerous from the radiation. Awesome. Oh, okay, Smile and Style. Yeah, Smile and Style. Soon maybe I'm going to blind somebody. I haven't seen our good friend Oren for a while, but I hope he'll join us. I hope I don't blind anybody with the brightness. This one's not as bad, right? However, if we go in and we take a closer look, we can see a lot of those dark spots, those sunspots. If we go and take a closer look at one of them, you'll actually see that they're not really that dark. They're actually quite bright. The difference is, and we're going to turn the lights down a little bit, the difference is that the stuff around them is actually much brighter and much hotter. So the only reason the sunspots look dark is because they're a little bit colder than the rest of the sun, right? But if we zoom right in, you can see they're still bright, they still glow. So that's what a sunspot looks like. Hey, Violet, thanks for joining us. Nice to see you. Well, or nice to read the words that you're typing, but I'm glad you could join us today. So those are sunspots. That's the solar wind. This is basically what stars have on them. They do some other crazy things too, but this is the sun today. The sun has been around for 5 billion years. A very long time. And I'd like to show you kind of how it was born and where it was born. The best place to look at for when the sun was born is to actually fly out to a good familiar friend. I don't know if I've shown this to you before, but this, what we're going to go see is the Orion Nebula. Why did I spell that wrong? Whoa, that was weird. Got a little bit of a hiccup there. Okay, let's go to the Orion Nebula. A nebula is a place where stars are born. In our Milky Way galaxy, oh, thank you for liking the video, Jackson. You're always the first one to do it, so I always know it's you, which is wonderful. This is called a nebula. It's actually a big clump of dust and gas in the Milky Way, in the galaxy, and that dust and gas collapses into stars. It shrinks down and makes stars. And when it makes new stars, you can see there's a bunch of stars in here already. When it makes these new stars, their light starts to shine, and they cause all this gas and dust around them to glow. They cause them to glow. And if we look actually kind of right in the middle, if we dim it down a little bit, in the middle you can see these new stars that were all born together. So you can see the stars, you know, stars are pretty big, but we can see the 7 of them very, very close together here inside this giant nebula. So when you see a nebula in the sky, oh, thanks for the comments and the likes and the subscribes too. That's really nice. Always happy to have followers, right? Oh, that's awesome. And I really love, more than anything, I love that you're chatting with me, because it makes it a lot nicer for me when I'm doing a program for you, right? To know that you're there. So this is what a nebula is, and this is where stars are actively being born. Now, when they're actually born inside the nebula, here's what's really happening. Let's see how the sun was born. And now it's, I always have to say the title's in French. I really should edit that out, but nothing else is in French. I'm going to just narrate it for you. So this is some of that gas and dust that we're seeing here. This is a nebula. And it starts to collapse. It starts to shrink. It gets smaller. Gravity pulls it into a ball, and it gets smaller and smaller. And as it gets smaller, 2 very interesting things happen. It starts to spin, and it starts to get flat like a frisbee. It starts to get flat like a frisbee. Idacia, I'm glad you feel good to be back. We're glad to have you back too. So we have a flat spinning frisbee of stuff, gas and dust and things that make up the Earth and the sun and all the planets. And in the very center, most of that stuff crashes together and gets hotter and hotter and hotter and makes the sun. I'll explain what's really happening in the sun pretty soon, but basically most of the stuff ends up in the middle. Most of the stuff ends up in the middle, and it gets really, really hot and makes the sun. Well, the stuff that's left over, that's what can become the planets, right? Amelia asks, how does the gas and dust have all those different colors? Well, I imagine you say you're thinking of the nebula that we looked at before. So we'll go back to that in a second, and I'll answer your question. And oh, hi, Callie. Nice to see you. How's your bird? Is your bird Kiwi was its name? I'm trying to remember if it's going to be joining us today as well. But the planets all form around the stars once they're made. And because all stars are born the same way, we're pretty sure that most of those stars have planets too. That's a little bit of what we talked about yesterday. So this is how a star is born and how planets form from what's left. But still, in our solar system, 99% of everything in the solar system is in the sun. And remember, here's the Earth. If we look at how big the sun actually is next to Earth, this is where we blind everybody, so just a heads up. Hey, Kiwi is here. Awesome. Hi, Kiwi. Kiwi is a cockatiel that Callie just got. That's very nice. All right, so there's... Oops. Uh-oh. I accidentally made a second sun. Almost. There we go. There's the sun. Very blindingly bright. 1 million Earths would fit into the sun. Okay, Amelia's curious about the colors of the nebula. So let's go take a look at that nebula one more time. So what's really happening is that the nebula is mostly made of what's called hydrogen gas. And hydrogen, when starlight shines on it, hydrogen actually splits apart, and you can kind of see through it. It doesn't block anything. So that's why it looks like the nebula is kind of hollow. But as you get further and further out, tiny little hydrogen atoms that were split apart, the hydrogen was split apart, it starts to crash back together and become hydrogen again. And when it does that, it actually makes a flash of light. So what you're seeing is on the outside, you see those glows, those flashes of light that are purple and blue and red. Purple and blue and red. Oh, you're wearing star barrette clips for the class. That's awesome. Very stylish. So this is, Amelia, this is why the colors tend to happen on the outsides of the cloud. And in the inside, all that hydrogen has been split apart. Some of the other elements do that too, but basically that's what happens is the star's light is so powerful, it starts to cause all that stuff to split apart, and when it combines back together, it glows. That's called a nebula. And actually, I'm going to show you a couple other nebulas that we have here. Here's a really big one. This is called the Tarantula Nebula. This is one of the biggest known nebulas, star-forming regions in the sky. I think it is the biggest, actually, which is kind of cool. So you can see lots of stars are being born in these little pockets, and their light is shining, causing this gas and dust to glow. Okay. So, and this is, stars, you can form a lot of stars in this small space. Like we said, there are 7 or 8 big ones in here. This cloud is actually much, much bigger and can form hundreds or thousands of stars over its life. You're really welcome, Amelia. And then what happens over time is eventually all the gas and the dust gets sucked up by the stars. All the stars, they form their planets, and you end up with what we would call a star cluster. So if we go to the Pleiades, Pleiades is a star cluster, and that's kind of what happens to the nebula after a few million or 100 million years, is all the gas gets sucked up and you just end up with stars, like this. Now we still see a little bit of gas here. This is called the Pleiades cluster. But all those stars are pretty much starting to fly out on their own. And gradually, over time, these stars are going to start to get farther and farther apart. And they're going to leave each other, they're going to leave this cloud, and they're just going to become part of all the other stars in the galaxy that are just kind of floating out here. Every star started out inside one of these nebulas. And that's how stars are generally born. It's a little bit different for really big stars, but the main concept is pretty much the same. So yeah, that thing that we're looking at right now makes stars. So that's how stars are born. Now, there's a lot of differences between different stars. And one of the biggest differences is their colors. So if we go and we take a look at stars after they're born, a star is really a balance. It's a balance, okay? So here's all the different types of stars, all the different colors, and it's based on temperature, which we're going to talk about in a second. Oops, I didn't want to go that close. But basically, when we look at a star, if we go back, actually, let's just go back to Space Engine for a second. We go back to Space Engine. We go back to the sun for a second. Let's just talk about the sun for a sec. I did want to actually tell you what's happening inside a star. Okay, this is a little bit more advanced for some of our older kids, but hopefully I'll at least give you a bit of an explanation for it. So the sun shines because it's like a big bomb that's exploding 1,000,000 times a second. What's happening is inside the center of the sun, tiny little hydrogen atoms are smashing against each other again and again and again. They're hitting each other again and again and again, faster and faster and faster. This is as the star is forming, as the sun is forming. And they hit each other faster and faster and faster until they start smashing into each other 1,000,000 times a second. I can't clap my hands that fast, but 1,000,000 times a second. And when they do that, they eventually, finally, fuse together. They stick together and they become a new thing. They become helium. Hydrogen turns into helium. It's called fusion. Fusion. And that fusion, when those atoms stick together, they explode like a big bomb and release a whole bunch of energy, which then starts other atoms around them fusing, and others fusing and fusing and fusing. It's a chain reaction that makes the star. And then you end up with a star like the sun, which today has been exploding like a nuclear bomb for over 5 billion years. That's what a star is. It's a big bomb. And stars are a balance of two things. They're a balance of all that heat and pressure of that explosion pushing out, and gravity from the weight of it pulling in, right? Everything that has weight has gravity. Everything that has mass has gravity. You and I have gravity, but we're much smaller than the Earth and the sun. So we have very, very little. So a star is being pulled in by gravity and pushed out by pressure. That balance is really, really important for how big a star is and how hot it is, okay? So all these different types of stars that we see here, a lot of it depends on their weight, but the real reason they have different colors is because of their temperature. Oh, Abigail likes auroras, huh? Well, maybe if we have some time at the very end, we'll take a look at an aurora, because auroras happen because of stars. Or I guess, Abigail, you're saying you like these as well. You like the wind coming off of it too, which is kind of cool. Okay, so here's our first type of star. This is a red star called an M star. Okay, it's the coldest one. Red stars are the coldest. They're still very hot. They're 3,000 degrees. That's really, really hot. That's hotter than your oven at home at maximum setting. Very, very hot. Well, I know we have a lot of people who really love auroras, which is nice because that's kind of why I'm doing the Aurora program in May, which is going to be really fun. Abigail says, yes, is there wind in space? Yeah, all of the stars make their own wind like this. And the solar wind, it's called the solar wind, travels through space all the time. It's a little bit different than the wind that we're used to. It's a little bit more dangerous, but it's always there. And when astronauts go into outer space, they have to be really, really careful. And spacecraft have to be protected from this solar wind because it can damage electronics. It can break computers. It's really dangerous, honestly. Luckily, we're protected from it. And we'll talk more about that when we eventually get to the Aurora program. So anyway, these are the red stars, the coldest ones, 3,000 degrees, just like the red flames in a fire. Thanks for that question, Abigail. That was a good one. So let's keep going. Hotter than red, we get orange. Orange stars like this one, this is type K, is they're about 4,000 degrees, a little bit hotter, still orangey. And then we get up to G-type stars. This is our sun. Our sun is a G star. It's 5,500 degrees, pretty hot, and it looks a little bit yellow, maybe even a little bit white. Okay, so that's your type G star. Don't be scared of stars, Jackson. There's so many good things about them. They're very far away, too. As we get a little bit hotter, we get to an F star. This is a yellow-white star that's around 6,000 degrees. We're getting hotter, they're getting brighter, and they're also getting a little bit heavier. Then we get up to the really fun ones. This is a type A star. It's white. Its temperature is over 10,000 degrees. They're very, very hot on the surface. The brightest star in our night sky, called Sirius, is a type A star. Then we get to the really fun ones. I like the two hottest ones because I love the blue colors. This is type B, B for blue, right? 20,000 degrees Celsius on the surface. Very, very hot. Very, very hot. Stars do give us light, totally. And actually, Smile and Style, stars are things that make their own light. That's what's different between a star and a planet, right? Stars give off light. Planets reflect light. Planets are when... The reason we can see planets is when light hits them and bounces off. It's like the light that's hitting my face right now. I've got a little light here. So watch this. Oh, it didn't do anything. Did I turn it off? No, I didn't. Yeah, okay, here you go. Watch. Dark. Light. Right? So the light from the star, the sun, this light is bouncing off of my face, and that's why you can see me look a little bit brighter, right? It would look bad if I was that dark. So that's kind of what's happening with planets and stars. How is it blue? Asked the Roth family. Well, blue is the hottest flames in a fire. When you see a campfire, the hottest flames in the fire are blue. The color really does depend on their temperature. So this star is 20,000 degrees. It's so hot that it's glowing blue. And there's one more star, one hotter. Those are the type O stars. They're so hot that they're almost like a purpley color. Very, very beautiful. 30,000 degrees. The heaviest stars in the universe are this color. Okay. So these are all the colors of stars that we have. O, B, A, F, G, K, M. Those are all the different types. And so every star falls into one of these categories based on their color. There's no other colors, no green, unfortunately, no purple, although O is kind of almost purple, but pretty cool colors though. So every star in the universe is one of these colors based on their temperature, right? Their temperature. So now what's going to happen to the sun? As the sun gets older, what's going to happen? Well, the sun is going to change a little bit. So let's go and, what's the best place? Let's actually do it in here. Let's do it here. So let's go to our solar system. Now, our sun is a pretty big star. We talked about how what it's doing is that it's turning hydrogen into helium, right? Those little hydrogen atoms are smashing together and making helium. And if we go back to, it actually looks better in Space Engine, so we'll go here. So hydrogen turns into helium, releases a bunch of energy, a bunch of heat, a bunch of light. That's what lets us see the sun as a star, and it keeps burning. But there's only so much hydrogen. What happens when the sun runs out of gas, runs out of fuel, just like a car running out of fuel? Well, the same thing happens to all stars. All stars actually run out of fuel. And I'm actually going to go back to our star types for a second, because all of these stars will eventually run out of fuel. And the ones that will run out faster are the hotter ones, right? Think of the hot stars, the blue stars, as like a tank, right? A tank burns a lot of gas because it's really big and it needs a lot of power, right? Needs a lot of power. So it uses a lot of gas really, really fast. So blue stars burn through their fuel very, very fast, and they don't live for very long. Red stars burn very, very slow. They're like a very small car that's even electric. So it puts in a little bit of gas and it goes for a very long time. So red stars, they live for a really long time. So blue stars don't live for very long. Red stars live for a really, really long time. So stars that tend to be younger and live faster are blue, white, yellow. Older stars that live longer are yellow, orange, red. That's the big key. So what happens though when the sun burns through all of its fuel? Well, when it runs out of hydrogen, it's just going to stop, but not for very long. When the sun runs out of fuel, when it runs out of gas, it's not going to burn anymore. And remember how we said it's pressure going out, gravity pulling in. Pressure going out, gravity pulling in. If there's no fuel, there's no more pressure. Gravity pulls it in and the sun starts to shrink. The sun is going to shrink and get smaller and smaller and smaller and hotter and hotter and hotter until it gets so hot that something amazing happens. The tiny little bits of helium, right? No more hydrogen. The next bits, the helium in the center of the sun that are smashing into each other again and again and again, they fuse. And when they fuse, they release even more energy than the hydrogen. And so the sun is actually going to get bigger. The pressure gets stronger. The heat gets stronger. The gravity is the same. So the sun gets bigger, bigger, bigger than it was before. It's going to turn into what we call a red giant. And so we're going to make it big. Where's the composition, maybe? Radius. Yeah, let's do... There we go. About 100 times bigger than it is now. And it's going to turn red. So that's what's going to happen to the sun. It's not going to happen for about 4.5 billion years. Quite a long time. Quite a long time. Almost 5 billion years. The sun is going to get big and it's going to get red. It's going to turn into what we call a red giant. And as you can see, it actually swallows up. It's actually going to get bigger than this, to be honest. So let me make it even bigger. Composition. Let's make it even bigger. Oh, a little bit too big. That's pretty accurate because it's going to swallow up Mercury and Venus and Earth and probably Mars as well. Are smaller stars hotter? Not usually. Smaller stars tend to be a little bit cooler. Just because they're smaller, when they're smaller, they have less weight. Stars that are smaller have less weight, which means they have less energy to begin with. and less gravity. So they're smaller, they have less force outward, less to push outward, less energy pushing outward, less gravity pulling inward. So they're small, they tend to be very red and cold, and they tend to live a very long time. Think of it more like, instead of smaller, think about lighter. So heavier stars burn faster. Lighter stars burn slower. That's the big key. Okay. And what is a black hole? We're going to eventually cover that. We'll cover that a little bit later when we talk about stars dying, because that's how we make it a black hole. And I'll explain what it actually is too. Okay. So here's our red dwarf. This is what the sun is going to become in about 5 billion years. So now it's not burning hydrogen anymore. It's burning helium. And this can happen a few different times. If the sun eventually runs out of helium, it's going to shrink down again and burn another element. And burn another element and burn another. And this can happen again. Callie asks, is our sun considered big or small? Also, how is your baby doing? Callie, the sun, believe it or not, the sun is a small star. The sun is a small star. I'll show you some other stars pretty soon once I get finished talking about this, and then we'll look at the sizes of different ones. And the baby's doing well. He's smiling at me and at his mother. He's got big blue eyes, and he's really, really fun. It's kind of neat being a dad. I'm pretty happy about it. I'm not sleeping very much, but that's okay. I don't feel too bad about that. The sun, believe it or not, is pretty small, right? Idasi, we think of it as big, right? Here, it's big. Like, this is a big size star when it becomes a red giant. But at its original size, like when it was, quite a bit smaller, maybe about 1/10 of that size, when the sun was actually its original size, that's pretty small. Okay, so the sun, and actually let's play and see what happens. Oh, I made it too hot. Let's see. That's better. That's about the right temperature. So you know what we're seeing too? Callie says that's great news. Thanks a lot. You know what we're seeing too is when we change the size of the sun, its temperature changes too, right? If we make it smaller, see how it gets hotter on the surface? It turns white. If we make it even smaller, it's going to start to turn. Oh, maybe not. I was hoping it would turn blue or something. Oh, there we go. So see, it actually turns blue or white. So a lot of it is tiny for a star. A lot of the color has to do with how much total energy the star is putting out and how big it is. Because what it's really doing is all the heat that's coming out of this star is being spread over the entire surface, right? Like the surface of a ball. If the ball is bigger, there's more room for all that energy to spread out, and it's colder, so it looks more red. So the biggest stars actually tend to be some of the coldest, which is kind of weird, right? But we'll talk about that in a second. So let's see, where was I going with this? Ah, yes, here, this picture. The sun and other stars can go through this process again and again, where they burn one element, one type of fuel, and turn it into something else. So they'll turn hydrogen into helium. And then they'll turn helium into carbon, and carbon into oxygen, and oxygen into neon, neon into magnesium, magnesium into silicon, and silicon into iron. This is what they do. Stars are like giant engines that make all of the little elements that make up the world. And you and me. Emily, thanks. She says, hope I can get more sleep. That's okay. It's one of those things, I'm not sleeping very much, but I'm still having a lot of fun. So it's okay. So if the sun was hotter, it would be blue. Think of it like this, Idasi. The sun, if it was smaller and it still put out the same amount of heat, if it was smaller, it would be blue. If it was bigger, it would be red. It's still putting out the same amount of light and heat and energy. But if you made it bigger, it would be colder on the surface. The whole surface, there'd be more room for all of that heat and all of that energy to spread out, and that would make it look red. If it was smaller, there's less room for all that heat to go together, so it would look hotter. Okay, and that's a little bit. It's a tough thing to understand. It really is. But this is what stars do: is they gradually burn Over billions of years, they burn through all these different elements. They make all of these elements. Jackson, happy belated birthday. They make all these different elements, okay? And eventually they reach a stopping point, which we'll talk about pretty soon. But let's go and see some of the sizes of stars. Let's go see some of the sizes, because I know we want to talk about those too. So our sun, like I said, was a small star, and I'm going to not blind anybody this time, hopefully. But here's some other stars. There's actually stars that are smaller than the sun, like this one. This is called Proxima Centauri. This is called a red dwarf star. About 8 out of 10 stars in the whole universe, 80% of all the stars in the entire universe are these ones. These little red stars called red dwarfs. And then there's the sun. And then here's a bigger star, the brightest star in the sky. This is Sirius, the type A white star. Quite a bit bigger, quite a bit hotter on the surface, right? And we can get bigger than this too. Let's go to Spica. Spica is a bright blue star. And by the way, these are all stars in our sky that we can see, except for Proxima. It's too small. But we can see Spica, a bright blue star, so very, very hot on the surface, but also heavier and bigger. It just has more, energy to work with. Yeah. I'll think of a good analogy for that pretty soon. Nice emojis, Emily. And they get bigger than this too. Here's Arcturus, a big orange giant. Or Rigel, a big blue giant. These stars are so hot, like Rigel is so hot and so heavy, it's burning through its fuel really, really fast. And then we get up to the biggest stars, remember, are red. They're called red supergiants. Stars, the second biggest star that we know of is about this big. It's about this big. So as stars get so big, they're so huge that all the heat and energy and light that comes out of them spreads out over this massive area and becomes, it makes the star actually kind of cool. And not just cool, but like colder too. Too bright? Yeah, sorry about that. So the biggest stars tend to be red. I really should find a way to dim the lights. Like, let me see if I actually have an option for that, because I'm kind of curious. Graphics maybe? Glows? Oh, does that help? That kind of helps. Resolution, effects quality. I'm going to turn it back on for a second, because maybe we can... No, that didn't help. Weird. Well, I mean, that helps, right? That's a bit less bright. I think I like this better, to be honest. It's still bright, but it's not blinding. And they actually look like they're in space too, right? So that's kind of nice. I think I like having that option off. Look at that. We figured it out. So these are all real stars, right? And they all have those different colors. And all of these stars are going through this process. They're going through burning one element, then burning another, and changing their size and changing their temperature, getting bigger, getting smaller, growing and shrinking, right? Like if we start a new simulation, we can take a star like Rigel, and Rigel will eventually grow a lot bigger. It's still pretty big right now, but we can make it composition, we can make its radius, we can increase it to 10 times its size. Ooh. Oh no, I blew it up. That was an accident. Let's try that again. See, this is why we experiment. It's kind of fun, right? Let's say maybe Sirius then. That's a better one. It's quite a bit smaller, but okay, there we go. And let's make Sirius even bigger. So let's see if we can make it grow to... There we go. What's going to happen to it? There it goes. See, it cools down. Oh, no. Oh, can't see. Thank you, Emily. I'm sorry. Here I was just kind of rambling on. It's amazing that I do that like literally every time. Hi, Emma. Emma says, can you put Earth beside the biggest star for us to see? Absolutely, I will. Let's do it. So the biggest star, this one. Whoop, there it is. And let's pause. Let's put the Earth next to it. I'll put it over here. All right, so let's go see the Earth. And there's the biggest star. So just to kind of put it in perspective, there's that tiny little dot of the Earth right next to that gigantic, huge star called UY Scuti. That star is about 1 trillion times as big as Earth, or like 1,000,000,000,000. Pretty huge. You can barely even see the little dot of the Earth, right? Because that star is so gigantic. There you go. Kind of cool, right? So let's actually do what I was trying to do before, and zoom out a bit, and let's put let's delete you. No, delete, please. There we go. All right. So let's add what am I doing here? Let's add Sirius, that bright white star. Ooh, too close, too close. There it is. Okay. And what we do is you know, as Sirius goes through all of these different transitions, it's going to get bigger and then smaller and then bigger and then smaller, and we'll see what it actually looks like if it was 10 times as big. Watch what happens. It's 10 times as big, and it cools down and turns yellow. So it eventually, because it's growing and it's got the same amount of heat, it is a different color. And we can do the same thing again. Whoop. And now it's going to get even redder, because you're spreading out that heat over a larger area. Okay. So that is, that's what happens to red stars, or to bigger stars too. They grow, they get bigger. So eventually what happens is the star goes through all of these different layers until it gets to iron. Now when it gets to iron is very different. Iron, instead of, when iron smashes together into other iron to stick together to make a new element, it doesn't actually explode. It actually takes extra energy. It doesn't make energy, it takes it. It sucks in a little bit. And when that happens, a star will actually start to reach the end of its life. And it'll start to shrink down smaller and smaller and collapse. Now, when the sun does this, the sun is eventually, oops, where's the sun? Let's put it there. Let's pause. The sun is eventually going to shrink down and get very small and turn blue. That's what's going to happen to the sun. But as it does that, all of its outer layers, all of these other layers that it made, are going to get puffed out. Yeah, iron is a greedy element, right? All those outer layers are going to get puffed out, and the sun is going to turn into something absolutely beautiful. It's going to turn into this. This is called a planetary nebula. Planetary nebula. In the very center of it is what's left of the sun, which is where is it? Which is what's left of the sun is this little star. But all those elements that were inside the star, all of the hydrogen and helium and carbon and oxygen and neon and magnesium and silicon and iron, are all going to get puffed out into this cloud, into this new nebula. And all those elements are going to go and fly out into space, and they're going to become part of new stars and new planets, and maybe even life. So what that means is that everything that makes up you and me, everything that you breathe, everything that you touch, everything that you are made of, was all inside a star a very long time ago. This is where all those elements are made, inside stars. And today, when we look up in the sky, we still see new elements being made, being puffed out into space, and those elements go into form new stars someday and become part of the stars, become part of the planets, and become part of you and I. That's what happens to stars like our sun when they die. Everything in the universe gets reused. That's a great way to think about it, Amelia. I like that. The universe is like excellent at recycling, right? So this is what happens to small stars like our sun. And what's left over, we're going to look at that. When the sun eventually does sneeze and puff out its outer layers, it makes a star that we call a white dwarf. A white dwarf is about, let me show you how big it is, or rather how small. It's about the size of the Earth. That's a white dwarf star. So pretty similar in size as the Earth. But if you took a spoonful of that star, of this white dwarf star, it would weigh 5,000 pounds. So a lot of stuff is still crammed into this star. But it's just burning. It's never going to turn into anything else. It's just going to get colder and colder and colder over time. It's going to take a long time to happen, but as it gets cooler and cooler, it's going to change colors from blue again through to white, through to red, but stay very small. And then eventually it's going to just stop glowing altogether and become what we call, what we think will become a black dwarf. A black dwarf, which is basically just a dark leftover of a star. Now, we don't think that there are any of these in space yet because they actually take a long time to cool down. But this is what will happen to the sun eventually. It'll turn into one of these. It'll puff out its layers into one of these called a planetary nebula. Planetary nebula. And it'll become about the size of the Earth. Pretty amazing. Pretty amazing. That's what's going to happen. But not for 5 billion years. So we don't have to worry about it anytime soon. So that's what happens to the sun. That's what happens to a small star. It dies with a sneeze. But big stars, they die differently. When a big star is making all of these elements, the star's much bigger, right? So if we go back and look at, like, let's pick one of those big stars. Maybe Rigel. I think Rigel was a good one. So we'll go back here, and we'll get rid of that, and we'll get rid of that, and we'll bring up Rigel. Big blue star, right? A lot bigger than the Earth. A lot bigger than the sun. Like, let's put the Earth and the sun in here too, just so we can see it. There's the Earth all the way down there. The sun right about there. Right, so there's the sun, and there's, yeah, the sneeze. I like it. Smile and style, I like it. So there's the sun, and then there's the big blue star, Rigel. Now, when the big star eventually runs out of fuel, again, remember, it is a balance of pressure pushing out and gravity pulling in. When that really big star reaches iron, and it starts losing the ability to burn fuel, there's no more fuel, nothing to keep the star going, the star starts to shrink. The star starts to shrink. Now, when that happens, the star's pretty big, right? So gravity wins, there's no more pressure pushing out, it starts to shrink down, smaller and smaller and smaller. And what happens is the edge of that star, the ends of this star, as they shrink down more and more. Oh, this is a good question. Callie asks if you know how many of our sun can fit into that star. If I had to guess, just looking at it, I would say it's probably about 100 wide, so probably about 1 million. Probably about 1 million of our sun could fit into this star, Callie. So thanks for that question. So let's go back to this for a second, right? The star starts to shrink. And because the star is so big, it shrinks really, really fast. The edges of the star start to collapse into the center almost as fast as the speed of light. They go really, really fast. And finally, when they get all the way to the center, they rebound like a big collision, like a big just ramming into a wall. They hit a wall, and then they explode. And when a star like this explodes, it's called a supernova. This is a supernova. And this one I'm actually going to turn the glow on for, because it's pretty awesome. It's pretty bright. So A supernova is the explosion of a big star that has started to collapse because it runs out of fuel. It collapses down, rebounds, and explodes. And this explosion, this supernova, is so big and so bright and so powerful that you can see it from across the universe. If one of the stars in our sky exploded like this, it would be so bright that you could see it in the daytime for 2 weeks. That's how bright it would be. You'd have the sun and you would have another star. Like imagine, we look at the night sky and you see all these stars. One of them, if it exploded, it would be so bright you would see it in the daytime, or it would make the nighttime so bright that it'd be brighter than the moon. Callie asks if we would be able to see it with our bare eyes. Absolutely. Absolutely. It would be super, super, super bright. When these stars explode, they can be brighter than millions and millions of other stars put together. So it's the most powerful explosion you can possibly imagine. And what I often tell people is try and imagine the biggest explosion that you can, right? Like imagine, like what I think of is I'm like, okay, what if we had a ball of dynamite as big as the Earth and it blew up next to my face? That'd be pretty bad, but that's a big explosion. However, a supernova is still bigger than that, still more powerful than that. And that explosion destroys everything around it. As you can see, there's not much left. Pretty awesome. And very, very bright. So, believe it or not, astronomers, every year, we see thousands of supernovas around the universe. So let me see if I can show you some. Here's a bunch of other galaxies. And you see all those twinkles? Those are stars exploding in those distant galaxies. The star explodes and it's so bright that we can see it across the universe. That's what you're seeing. Those exploding stars. That's kind of cool, right? I think last year astronomers found 800 of them exploding in other galaxies. And after they explode, they look a little different. Here is a really cool shape. This is called the Crab Nebula. This is a star that exploded as a supernova 1,000 years ago. 1,000 years ago it exploded, and this is what the explosion looks like today in the sky. Again, this star was so bright when it exploded that 1,000 years ago they could see it. It was really bright. And it's kind of comparable to our supernova, right? Like they kind of look similar, right? That's what we're seeing. Kind of neat. So what happens though? After the star explodes, you know how we talked about all those elements moving out into outer space? All those different elements, when you have a supernova, you actually make more of them. You don't just make hydrogen and helium and oxygen. You make heavier stuff like titanium and uranium and plutonium and all the things that are on the periodic table that are really heavy. That's what a supernova does. It's like a big particle smasher too. But what's left? After the star explodes, there's actually stuff left, believe it or not. So let's go and take a look at what we can end up with. So let's go back to what we had before. We had the Earth, and we had a white dwarf star, right? Which is what the sun can become when it sneezes. So there's our white dwarf star. If you have a supernova, one of two things can happen. What's left over can shrink down into a what's called a pulsar or a neutron star, which is if you took the whole weight of the sun and crammed it into a very small space, only about 10 kilometers across, you would make something like this. This is a pulsar. This is technically a neutron star, but I'll show you a pulsar. And these are so heavy that if you took remember when we said this one, if you took a spoonful of this star, it would weigh 5,000 pounds. If you took a spoonful of this star, it would weigh as much as a mountain. billions and billions of pounds, millions of tons. It would be so powerful, so heavy. And when we see these, they're actually, I'm going to bring up a pulsar. Binary pulsar. So one of the things that okay, I know this is kind of crazy. It looks like a dance party, doesn't it? I'm just going to get rid of one of them, and we'll slow it down a little bit so we can see. There we go. So what you're seeing here is a neutron star, like the one we were just looking at. And what happens? It's like vibrating. It's so powerful. But what happens to them is when you make something smaller, like if you take a star and make it and shrink it down, it actually starts to spin faster. It's the same as if you think of a figure skater, right? When they're about to jump, they stretch their arms out, and then when they jump, they bring their arms in and they spin faster. Okay? That's kind of what the stars are doing. When the star shrinks down, it spins faster. And so what's happening with this is you take that big star, like the sun, well, bigger than the sun, and you shrink it down. After it explodes, what's left shrinks down into something smaller than a city, and it spins. They can spin up to 1,000 times a second. Imagine them spinning 1,000 times a second. That is called a pulsar. And I want to just get to the right spot. So, there? Close. Let's speed it up a little bit. So you see that flash? This is what we see from Earth. When we're far away, you can see a little flash. You see the little pulse? That's why it's called a pulsar, is you see this little pulse of light, of energy come out. This star is spinning so quickly that it's got these big jets shooting off of it. And that's what creates the pulse of light that we see. So that's a pulsar, and this is what happens when a big star explodes. However, there's one more thing that can happen. Let's go back to what we had before. We had our white dwarf star. So Earth, our white dwarf star, and why is that on? That shouldn't be on. We have Earth, our white dwarf star, and this is our pulsar or our neutron star. If what's left, if after the star explodes, whatever's left, if it weighs more than 3 times as much as the sun, 3 solar masses, it collapses down even farther and becomes a black hole. A black hole is called a black hole, and this is for the Roth family who was curious about this. A black hole is called a black hole because it has so much gravity. It's so crammed in. It's got so much stuff crammed into a small space that no light can actually escape from it. It's like a star that doesn't give off light. Any light that tries to get out actually just ends up going in circles inside. Anything, and this is why you can see that it's kind of like bending light around it, right? Like when you put it in front of a star, it bends the light a little bit. Is because any light that gets too close falls in. And that's what makes it dark. What does it do? It doesn't really do anything. Black holes just kind of float out in space. And sometimes they can suck up stars, and they look really cool. Sometimes they just float out in the darkness of space, not really doing anything. Violet asks, was the Rosette Nebula made in the same way? The Rosette Nebula is much more of like how stars were born. So if we go back to the Rosette in Stellarium, it's over here. There it is. So the Rosette is what happens when a new star is born, right? It's a little bit different. There's actually, as you've seen, there's actually a few different types of nebulas. There's a star-forming nebula, like this one. And actually, let me show you the few examples. So there's star-forming nebulas like that one. There's supernova remnants, like the Crab Nebula, this one. The supernova, the star that exploded. There's... where was the other one? There's planetary nebulas, like this one, which is when a small star sneezes. And those are the main three types. So here's the three of them. Again, one more time. Where stars are born, star-forming nebula. When a small star dies with a sneeze, called a planetary nebula. And when a big star dies in a supernova, called a supernova remnant. Those are the three main types of nebulas. So the rosette is the first type, the star forming. Okay? But what happens, though, with the other two, what happens with the Crab Nebula, with the supernova remnant, is all the stuff that makes up this nebula can actually become part of one of these new star-forming nebulas, and all those elements become parts of new stars. All right? That's how it works. So that's basically the life and the death of stars. Those are all the things that it can become. Stars, they start out, and look at this, I'm actually going to be on time for once. Can you believe it? That's never happened before. Well, it sort of happened yesterday. So the Rosette Nebula, yeah, that's really nice, right? When stars are born, all that dust and gas collapses into the star and makes planets. When the star starts to glow, it pushes away all the gas and dust. Oh, the Rosette Nebula is your favorite. Nice. It pushes away all the gas and dust and causes it to glow. As the star goes through its life, it burns all these different types of fuel. And bigger stars burn through it faster. Smaller stars burn through it slower. And those small stars, and the big stars, when they eventually start to burn iron, iron stops them from living. I said I'd be over time today, right? I'm sure I could get to it. I'm being better, Jackson. I'm being better. So these stars eventually burn iron, and then they run out of life, and small stars like our sun eventually just kind of puff out and sneeze and make something like the Cat's Eye Nebula, a planetary nebula. And when they're gone, the star becomes a white dwarf star, like this one, this big one over here, the same size as Earth. Big stars, they explode as a supernova and can become a supernova remnant, like our Crab Nebula. And what's left inside the center of the Crab Nebula after that star dies, after that star explodes, we see one of two things, right? We see either a neutron star, which is like a pulsar spinning very fast and flickering, or a black hole, which we can't see at all. That is the entire life and death of stars. Big stars die with a bang. Small stars die with a sneeze. Stars are all born inside nebulas, and when they die, they make new elements that eventually are recycled into other stars. That's the life and death of stars. Do we have any last questions from anybody? Emily says, I have a cat that's an orange tabby. That's nice. What's your cat's name, Emily? What's your cat's name? Do we have any other questions? Anything else we want to know about the life and death of stars? If not, that's great. We've so far this week, we've talked about the Earth, Moon, and Sun, which was really fun. I like that one a lot. Yesterday, we talked about planets and exoplanets around other stars, and we just barely went over time. Today, we're right on time with the life and death of stars. And tomorrow, I hope to see you all again for galaxies across the universe. We're going to talk about those big collections of stars that all kind of work together to produce a really big structure, one of the biggest structures, a galaxy. Emily's, your cat's name Freddy or Fred. I like it. And Smile and Style with the black cat, Black Jackie. I like it. Very nice. Callie says Kiwi watched it all, is watching on my shoulder. That's awesome. I'm glad everybody's having fun with their pets, right? Pets are really nice, especially while we're at home, right? It's nice to be able to cuddle your pets and have them as company too, right? All right, my friends, it's 2 o'clock. We got to finish up. Thanks a lot for spending some time with me today. As usual, I hope to see you tomorrow. You can always send any other questions you have over my way at Astro in Action. Always nice to see you, and I hope to see you tomorrow. Everybody have a great day. Stay warm, and we'll see you next time. Bye-bye.